There we go. Okay, so today, first of all, it's our last Monday, our second to last live class. And so I just want to talk a little bit about the plan as we wrap things up this week. Um, let's try to make sure that we've got all our work done by Friday. And this week, I've got 3 things for you in Google Classroom. Uh, 2 of them are just continuing your work in Mathagon and Khan Academy. And then I'm asking for you to report on your overall learning and what you looked at in both of those, and submit those things. And then the last thing is just a survey about how things went in this class and what you liked or what you didn't like and that sort of stuff. And I just ask for your honest feedback on that. And then life will be good. And if you have anything that's missing, last night I sent emails with anything that people hadn't turned in. I got a lot of those things turned in already, so thank you for that. If there's still some stuff out there that you have not turned in yet, please do try to get that stuff wrapped up as soon as possible. Also, if you feel like, wait a minute, I thought I did that, let me know and I can double check things, and we'll see where we're at on those things. So anybody have any questions on any of that stuff? All right, so that's what we've got going there to wrap things up. Then today I want to focus on 2 things that I don't think get very much time in most math classes. And one of them is math anxiety, which is a very real thing for some people, for a lot of people. And so just a quick video about that. And then some things about the history of math and where some of these things started and how it developed and all that sort of stuff. There have been quite a few comments about that in the Mathagon responses and in other areas where I've asked for your thoughts. And so it's something that I think definitely doesn't get very much time in traditional math classes and what you learn in school. And I think there's a lot of really interesting stuff in terms of, well, why is this used for this thing, or when did this start, who came up with this idea, and so on. And so we'll just spend a little bit of time with that. I found 3 videos that I think do a nice job of talking about some of those different areas. And then there's one on the math anxiety. It's about a half hour total for the 4 videos. And what I would like to do is similar to what we did, I believe it was last Monday, where we watched a video together and then we just went around and everyone shared something that they found interesting or something they learned from the videos, and we'll just do it all in one chunk. So after we watch the 4, then we'll spend time, we'll start with a volunteer, and then they'll call on the next person and everyone will get a chance to share. And it's a great way to hear from everyone and see people, and I thought it went well. So I think that'll be a good thing for us to do again today. So we'll do those, and then we'll open it up at the end for questions on anything that you have, and then we'll probably be out of time. So does anybody have any thoughts or questions before we start in? All righty. I'm going to start the first video and then pause it just to make sure that everybody can hear it okay. Make sure we've got all those settings right. But the first one is the math anxiety one. And as you watch all of these videos, I would encourage you to maybe jot some things down. As I taught this in the previous group today, I wrote some stuff down as well. Hopefully you'll pick up and see some things that you think are interesting and so on. So without further ado, let me stop sharing this one, and then we will, I'll share my screen here and we will dig into the videos. All right, first one, math anxiety.
When French mathematicians
All right, can everybody hear the sound okay? Can we hear it? Good?
Yes.
All right, fantastic. Here we go.
Laurent Schwartz was in high school, he started to worry that he wasn't smart enough to solve math problems. Maybe you know a similar feeling. You sit down to take a math test, and you feel your heart beat faster, and your palms start to sweat. You get butterflies in your stomach, and you can't concentrate. This phenomenon is called math anxiety, and if it happens to you, you're not alone. Researchers think about 20% of the population suffers from it. Some psychologists even consider it a diagnosable condition. But having mathematical anxiety doesn't necessarily mean you're bad at math. Not even close. Laurent Schwartz went on to win the Fields Medal, the highest award in mathematics. People might think that they're anxious about math because they're bad at it, but it's often the other way around. They're doing poorly in math because they're anxious about it. Some psychologists think that's because math anxiety decreases a cognitive resource called working memory. That's the short-term memory system that helps you organize the information you need to complete a task. Worrying about being able to solve math problems or not doing well on a test eats up working memory, leaving less of it available to tackle the math itself. People can suddenly struggle with even basic math skills like arithmetic that they've otherwise mastered. Academic anxiety certainly isn't limited to math, but it does seem to happen much more frequently and cause more harm in that subject. So why would that be? Researchers aren't yet sure, but some studies suggest that the way children are exposed to math by their parents and teachers play a large part. If parents talk about math like something challenging and unfamiliar, children can internalize that. Teachers with math anxiety are also likely to spread it to their students. Pressure to solve problems quickly dials up stress even more. And in some cultures, being good at math is a sign of being smart in general. When the stakes are that high, it's not surprising that students are anxious. Even Miriam Mizrakhani, an influential mathematician who was the first woman to win the Fields Medal, felt unconfident and lost interest in mathematics because her math teacher in middle school didn't think she was talented. So if you experience mathematical anxiety, what can you do? Relaxation techniques like short breathing exercises have improved test performance in students with math anxiety. Writing down your worries can also help. This strategy may give you a chance to re-evaluate a stressful experience, freeing up working memory. And if you have the chance, physical activity like a brisk walk deepens breathing and helps relieve muscle tension, preventing anxiety from building. You can also use your knowledge about the brain to change your mindset. The brain is flexible, and the areas involved in math skills can always grow and develop. This is a psychological principle called the growth mindset. Thinking of yourself as someone who can grow and improve can actually help you grow and improve. If you're a teacher or parent of young children, try being playful with math and focusing on the creative aspects. That can build the numerical skills that help students approach math with confidence later on. Importantly, you should give children the time and space to work through their answers. And if you're an administrator, make sure your teachers have the positive attitudes and mathematical confidence necessary to inspire confidence in all of their students. Also, don't let anyone spread the myth that boys are innately better than girls at math. That is completely false. If you experience math anxiety, it may not help to just know that math anxiety exists. Or perhaps it's reassuring to put a name to the problem. Regardless, if you take a look around yourself, the odds are good that you'll see someone experiencing the same thing as you. Just remember that the anxiety is not a reflection of your ability, but it is something you can conquer with time and awareness.
There's one down, that's the math anxiety. Now let's dig in and learn more about the history of math.
Human beings, from our earliest beginnings, have searched for solutions to basic problems. Building homes, measuring space, keeping track of seasons, and counting objects. Over 30,000 years ago, early Paleolithic people kept track of the passing seasons and the changes of weather for planting. To represent the passing of time, they carved tally marks on cave walls or slashed tallies on bones, wood, or stone. Each tally stood for one. But this system was awkward when it came to large amounts, so symbols were eventually created that stood for groups of objects. Sumerian clay stones have been found that date to the 4th millennium BC. A small clay cone was used for 1, a clay ball was used for 10, and a large cone stood for 60. Written records from around 3300 BC show that Babylonians inscribed amounts on clay tablets with a reed. They used a nail shape for 1s and a V on its side for 10s, combining these symbols to write other numbers. For example, Babylonians wrote the number 19 as. The ancient Egyptians used objects from their everyday life as symbols. A rod stood for 1, a cattle hobble was 10, a coiled rope was 100, a lotus flower was 1,000, and so on. The number 19 was a cattle hobble and 9 rods. The early Romans created a number system that we still see today. Along with other symbols, they used an X for 10 and an I for 1. By the Middle Ages, Romans were putting the I to the right of the X for 11 and to the left for 9. So they wrote 19 as XIX. All these creative number systems show groups of objects as well as individual objects. Some of the oldest human counting systems rely on fingers and toes, so they were based on 1s, 5s, 10s, and 20s. The Zulu word for 6 means to take the thumb of the right hand, meaning that all the fingers on the left hand had been added up and the other thumb was needed. Other systems evolved from commerce. The Yoruba in Nigeria used cowrie shells as currency and developed an amazingly complex number system. It was based on 20s and on the operations of multiplication, subtraction, and addition. For example, they thought of 45 as 3 times 20 minus 10 minus 5. Knots tied in cords and strings were used for recording amounts by many cultures, like the Persians. The Incans used a more refined version called a quipu, a thick cord held horizontally from which hung knotted string. The kind of knot the Incans used, along with the length and color of the cord, represented 1s, 10s, and 100s. In today's world, almost every industrial culture uses the numerals 0 through 9. But these symbols weren't invented until the 3rd century BC in India, and it took another 800 years for the idea of 0 with place value to be constructed. This big idea dramatically changed the face of mathematics. We humans have always shared with one another. When early cultures shared their food and water or wanted to divide their land in ways that were fair and equal, fractions gradually emerged as symbols for these fair share situations. The ancient Egyptians used unit fractions. Fractions where the numerator is 1, like 1/2, 1/3, and 1/5, and would add and halve these fractions. If they wanted to divide 3 loaves of bread equally among 5 family members, they'd first divide the first and second loaves into thirds. Then they'd divide the third loaf into fifths. Finally, they'd take the remaining 1/3 from the second loaf and divide that into 5 pieces. They wrote this as 1/3, 1/5, 1/15. Today, we would represent this sharing with the fraction 3/5. 3/5 of a loaf for each person, or 3 loaves divided by 5 people. The Sumerians and early Babylonians invented a number system of fractions based on 60 that we still use 4,000 years later. Our days have 60-minute hours and 60-second minutes, and our circles encompass 360 degrees. Chinese societies used an abacus with a system based on tens, although it had no 0. An early form of decimal fractions came from the abacus. For example, 3/5 would be 6 out of 10 on an abacus. The Chinese lovingly named the numerator the sun and the denominator the mother. It wasn't until the 12th century that common fractions with the bar notation that we use today were invented. Even then, these fractions weren't widely used until the Renaissance period, only 500 years ago. Throughout history, every culture around the globe has created inventive ways to calculate. To solve a problem, say 12 times 15, early Russian peasants used a system of doubling and halving. When an odd number, halved, resulted in a fraction, they rounded down. Then they added the factors associated with the odd multipliers. Ancient Egyptians relied on a doubling procedure until they produced enough groups. Then they added these groups to find the answer. Across Europe and Asia during the Middle Ages, the abacus was the handheld calculator of its day, but only very few people knew how to use it, usually wealthy merchants and moneylenders. By simply moving beads that each had place value, an abacus was a highly efficient way to compute. Then, the great Arab mathematician Al-Khwarizmi introduced the Hindu-Arabic numerals 0 through 9 into North America and Europe and created new procedures for computation. These algorithms could be written onto paper. Over the centuries, learning the algorithms became the hallmark of an education, as students were taught to compute long columns of figures, borrow and carry, and do long division efficiently and reliably. They could now keep records of these procedures and check results. Today, complex calculations are done with a handheld calculator. This means students need the ability to check the reasonableness of the answer and to have a rich repertoire of mental math strategies to do that. Most simpler computations, like 12 times 15, can be solved mentally using a variety of strategies. As we journey through the rich and vibrant history of mathematics, we can see how ideas and creations grew out of our very human need to solve the problems in our everyday lives. Through time, the mathematical explorations of men and women from around the globe have given us fascinating lenses that help us to mathematically view and make sense of our worlds.
So that's a bigger history. Now we're going to focus on just some of the math symbols and where those came from. So here we go.
In the 16th century, the mathematician Robert Recorde wrote a book called The Whetstone of Wit to teach English students algebra. But he was getting tired of writing the words is equal to over and over. His solution? He replaced those words with two parallel horizontal line segments because the way he saw it, no two things can be more equal. Could he have used 4 line segments instead of 2? Of course. Could he have used vertical line segments? In fact, some people did. There's no reason why the equal sign had to look the way it does today. At some point, it just caught on, sort of like a meme. More and more mathematicians began to use it, and eventually, it became a standard symbol for equality. Math is full of symbols: lines, dots, arrows, English letters, Greek letters, superscripts, subscripts. It can look like an illegible jumble. It's normal to find this wealth of symbols a little intimidating, and to wonder where they all came from. Sometimes, as Recorde himself noted about his equal sign, there's an apt conformity between the symbol and what it represents. Another example of that is the plus sign for addition, which originated from a condensing of the Latin word et, meaning and. Sometimes, however, the choice of symbol is more arbitrary, such as when a mathematician named Christian Kramp introduced the exclamation mark for factorials, just because he needed a shorthand for expressions like this. In fact, all of these symbols were invented or adopted by mathematicians who wanted to avoid repeating themselves, or having to use a lot of words to write out mathematical ideas. Many of the symbols used in mathematics are letters, usually from the Latin alphabet or Greek. Characters are often found representing quantities that are unknown and the relationships between variables. They also stand in for specific numbers that show up frequently, but would be cumbersome or impossible to fully write out in decimal form. Sets of numbers and whole equations can be represented with letters too. Other symbols are used to represent operations. Some of these are especially valuable as shorthand because they condense repeated operations into a single expression. The repeated addition of the same number is abbreviated with a multiplication sign, so it doesn't take up more space than it has to. A number multiplied by itself is indicated with an exponent that tells you how many times to repeat the operation, and a long string of sequential terms added together is collapsed into a capital sigma. These symbols shorten lengthy calculations to smaller terms that are much easier to manipulate. Symbols can also provide succinct instructions about how to perform calculations. Consider the following set of operations on a number. Take some number that you're thinking of, multiply it by 2, subtract 1 from the result, multiply the result of that by itself, divide the result of that by 3, and then add 1 to get the final output. Without our symbols and conventions, we'd be faced with this block of text. With them, we have a compact, elegant expression. Sometimes, as with equals, these symbols communicate meaning through form. Many, however, are arbitrary. Understanding them is a matter of memorizing what they mean and applying them in different contexts until they stick, as with any language. If we were to encounter an alien civilization, they'd probably have a totally different set of symbols. But if they think anything like us, they'd probably have symbols. And their symbols may even correspond directly to ours. They'd have their own multiplication sign, symbol for pi, and, of course, equals. If you enjoyed this lesson, we think you'll enjoy learning more about one of our favorite mathematical.
All right, so there's a little bit on math symbols, kind of some interesting stuff there, where some of those came from. And then the last thing is a bigger picture view of math. This is the longest one, but lots of stuff here and a number of things that people have looked at in Mathagon especially show up in this video as well. So last one here we go.
The mathematics we learn in school doesn't quite do the field of mathematics justice. We only get a glimpse at one corner of it, but mathematics as a whole is a huge and wonderfully diverse subject. My aim with this video is to show you all of that amazing stuff. We'll start back at the very beginning. The origin of mathematics lies in counting. In fact, counting is not just a human trait. Other animals are able to count as well. And evidence for human counting goes back to prehistoric times, with check marks made in bones. There were several innovations over the years, with the Egyptians having the first equation, the ancient Greeks making strides in many areas like geometry and numerology, and negative numbers were invented in China, and 0 as a number was first used in India. Then, in the golden age of Islam, Persian mathematicians made further strides and the first book on algebra was written. Then mathematics boomed in the Renaissance along with the sciences. Now there's a lot more to the history of mathematics than what I've just said, but I'm going to jump to the modern age and mathematics as we know it now. Modern mathematics can broadly be broken down into two areas: pure maths, the study of mathematics for its own sake, and applied maths, when you develop mathematics to help solve some real-world problem. But there's a lot of crossover. In fact, many times in history, someone's gone off into the mathematical wilderness, motivated purely by curiosity and kind of guided by a sense of aesthetics. And then they've created a whole bunch of new mathematics, which is nice and interesting, but it doesn't really do anything useful. But then, say, 100 years later, someone will be working on some problem at the cutting edge of physics or computer science, and they'll discover that this old theory in pure math is exactly what they need to solve their real-world problems, which is amazing, I think. And this kind of thing has happened so many times over the last few centuries. It's interesting how often something so abstract ends up being really useful. But I should also mention that pure mathematics on its own is still a very valuable thing to do, because it can be fascinating and on its own can have a real beauty and elegance that almost becomes like art. Okay, enough of this highfalutin, let's get into it. Pure maths is made of several sections. The study of numbers starts with the natural numbers and what you can do with them with arithmetic operations. And then it looks at other kinds of numbers, like integers, which contain negative numbers, rational numbers, like fractions, real numbers, which include numbers like pi, which go off to infinite decimal points, and then complex numbers, and a whole bunch of others. Some numbers have interesting properties like prime numbers or pi or the exponential. There are also properties of these number systems. For example, even though there's an infinite amount of both integers and real numbers, there are more real numbers than integers. So some infinities are bigger than others. The study of structures is where you start taking numbers and putting them into equations in the form of variables. Algebra contains the rules of how you then manipulate these equations. Here you'll also find vectors and matrices, which are multidimensional numbers, and the rules of how they relate to each other are captured in linear algebra. Number theory studies the features of everything in the last section on numbers, like the properties of prime numbers. Combinatorics looks at the properties of certain structures like trees, graphs, and other things that are made of discrete chunks that you can count. Group theory looks at objects that are related to each other in, well, groups. A familiar example is a Rubik's Cube, which is an example of a permutation group. And order theory investigates how to arrange objects following certain rules, like how something is a larger quantity than something else. The natural numbers are an example of an ordered set of objects, but anything with any two-way relationship can be ordered. Another part of pure mathematics looks at shapes and how they behave in spaces. The origin is in geometry, which includes Pythagoras, and is close to trigonometry, which I'm sure we're all familiar with from school. Also, there are fun things like fractal geometry, which are mathematical patterns which are scale invariant, which means you can zoom into them forever, and they always look kind of the same. Topology looks at different properties of spaces where you're allowed to continuously deform them but not tear or glue them. For example, a Mobius strip has only one surface and one edge, whatever you do to it. And coffee cups and donuts are the same thing, topologically speaking. Measure theory is a way to assign values to spaces or sets, tying together numbers and spaces. And finally, differential geometry looks at the properties of shapes on curved surfaces. For example, triangles have got different angles on a curved surface. And brings us to the next section, which is changes. The study of changes contains calculus, which involves integrals and differentials, which looks at the area spanned out by functions or the behavior of gradients of functions. And vector calculus looks at the same thing but for vectors. Here we also find a bunch of other areas like dynamical systems, which looks at systems that evolve in time from one state to another, like fluid flows or things with feedback loops like ecosystems. And chaos theory, which studies dynamical systems that are very sensitive to initial conditions. Finally, complex analysis looks at the properties of functions with complex numbers. This brings us to applied mathematics. At this point, it's probably worth mentioning that everything here is a lot more interrelated than I've drawn. In reality, this map should look more like a web tying together all the different subjects, but you can only do so much on a two-dimensional plane, so I've laid them out as best I can. Okay, we'll start with physics, which uses just about everything on the left-hand side to some degree. Mathematical and theoretical physics is a very close relationship with pure maths. Mathematics is also used in the other natural sciences with mathematical chemistry and biomathematics, which look at loads of stuff from modelling molecules to evolutionary biology. Mathematics is also used extensively in engineering. Building things has taken a lot of maths since the Egyptians and Babylonian times. Very complex electrical systems like aeroplanes or the power grid use methods in dynamical systems called control theory. Numerical analysis is a mathematical tool commonly used in places where mathematics becomes too complex to solve completely. So instead you use lots of simple approximations and combine them all together to get a good approximate answers. For example, if you put a circle inside a square, throw darts at it, and then compare the number of darts in the circle and the square portions, you can approximate the value of pi. But in the real world, numerical analysis is done on huge computers. Game theory looks at what the best choices are given a set of rules and rational players, and it's used in economics when the players can be intelligent, but not always, and other areas like psychology and biology. Probability is the study of random events like coin tosses or dice or humans, And statistics is the study of large collections of random processes, or the organization and analysis of data. This is obviously related to mathematical finance, where you want to model financial systems and get an edge to win all those fat stacks. Related to this is optimization, where you're trying to calculate the best choice amongst a set of many different options or constraints, which you normally visualize as trying to find the highest or lowest point of a function. Optimization problems are second nature to us humans, and we do them all the time, trying to get the best value for money or trying to maximize our happiness in some way. Another area that's very deeply related to pure mathematics is computer science, and the rules of computer science were actually derived in pure maths and is another example of something that was worked out way before programmable computers were built. Machine learning, the creation of intelligent computer systems, uses many areas in mathematics like linear algebra, optimization, dynamical systems, and probability. And finally, the theory of cryptography is very important to computation and uses a lot of pure maths like combinatorics and number theory. So that covers the main sections of pure and applied mathematics. But I can't end without looking at the foundations of mathematics. This area tries to work out the properties of mathematics itself and asks what the basis of all the rules of mathematics is. Is there a complete set of fundamental rules, called axioms, which all of mathematics comes from? And can we prove that it's all consistent with itself? Mathematical logic, set theory, and category theory try to answer this, and a famous result in mathematical logic are Gödel's incompleteness theorems, which, for most people, means that mathematics does not have a complete and consistent set of axioms, which means that it's all kind of made up by us humans. Which is weird, seeing as mathematics explains so much stuff in the universe so well. Why would a thing made up by humans be able to do that? That is a deep mystery right there. We also have the theory of computation, which looks at different models of computing and how efficiently they can solve problems, and contains complexity theory, which looks at what is and isn't computable, and how much memory and time you would need, which, for most interesting problems, is an insane amount. So that is the map of mathematics. Now, the thing I've loved most about learning maths is that feeling you get where something that seemed so confusing finally clicks in your brain and everything makes sense, like an epiphany moment, kind of like seeing through the Matrix. In fact, some of my most satisfying intellectual moments have been understanding some part of mathematics and then feeling like I had a glimpse at the fundamental nature of the universe in all of its symmetrical wonder. It's great. I love it. Making a map of mathematics was the...
Alrighty. Let me stop sharing that. We'll get to everybody's pictures here. So hopefully there were some things in there that you found interesting that you hadn't heard before. One of the things that I'll start by sharing is the 60 and why there's 60 minutes in an hour and 60 seconds in a minute. That 60 thing seems kind of weird, but it goes back a long time. So as I said, we'll have everyone get an opportunity to share something that they found interesting or that they wondered about or something that they learned. And it can come from any of the 4 videos that we watched. And then we'll take it from there. I enjoy hearing from each and every one of you. And so anybody want to volunteer to start? All right, Ayan, you're up.
There's such thing as math anxiety. I didn't know that existed. I thought it was just test anxiety. So.
Okay, and something that I jotted down from that one actually was how if we only have so much space to work with in our brain, and if we're using a whole bunch of it to be worried and concerned that we're not good at math and all that, then we actually have less brain power to work with, and that makes it even harder. So I thought, yeah, that's really interesting. And as a teacher, that's something that I am very aware of and want to help students to overcome and really focus on that growth mindset and the idea that you're not, some students are just absolutely convinced that they're horrible at math and that's the way it'll always be. And that's definitely not the case. So yeah, awesome. All right. Then you want to call on the next person?
I can choose.
Yep, you pick the next person.
Let's do James.
I found it interesting that animals can count, and I liked it when he talked about the topology in the mobile strip.
Yeah, I caught that animals can count thing too. I'm like, I need to maybe check into that a little bit more. But yeah, there's lots of areas of math, and many of those, the ones that maybe you haven't heard of before, are involved in math majors in college, topology and combinatorics and those sorts of things. Would be involved in a math major if you want to go to college for that. So awesome. All right, who's next?
Alani.
Some of the things I found interesting is just where some ideas came from. Like that the first book on algebra came from Persia, or that negative numbers were invented in China.
Yeah, and it's amazing how all of those things kind of came together around the world. And yeah, it just, I really didn't learn much about the history of math until I had a class in college that was the history of math. And there's so many interesting things and different ways that they went about those calculations. So yeah, very cool. All right, who's next?
Spencer?
I wrote down that game theory can be used in economics, psychology, and biology.
Yeah, very interesting. And with the power of computers these days, we look at something like Amazon, and they've gotten really good at predicting what people want to buy based on what other people that have bought the same stuff, and to then put those things in front of you and say, hey, other people that bought or looked at what you're looking at wanted and purchased this and that and the other thing, and using that big data and so on. So yeah, very interesting stuff. Awesome. Who's next?
Sir.
Hi. So all I had was how the people that found out about math, I guess, were only bored or lazy to keep counting, so they came up with math.
Well, and if you think about it, when you get to the bigger numbers that take a long time to make hash marks to count up to 100 and so on. So yeah, it kind of became a necessity to use some different symbols so that we didn't have to write those dash marks. And I thought the paragraphs of text that they showed, and then bringing it down to just the symbols and so on, holy cow, makes it so much easier for us to work with. And yeah, it in some ways came out of necessity to make things easier for us. All right, who's next?
Sona?
Is it me? Oh. I really like the game they play. I don't know what's the second movie we watched. Is it that they call the number like 1x is an NT. It's so good, like counting those numbers.
Okay.
And
Yeah.
also China too. The red dot thing.
Can you say that last part again? I didn't catch that.
The Chinese, they use
Okay.
number.
Yep. Yeah. Lots of different stuff. And again, that idea of all over the world, people were coming upon these issues of, oh, what about fractions? How can we represent those things, and how the different symbols for different numbers, and so on. So, all right. Next up.
Kaku.
Go away.
Why is she so sensitive?
Thank you. Okay.
Oh, they could hear.
Okay, so what I found interesting was how they started using the blocks of stones and the circle sphere rock thing to as they get higher at counting the numbers.
Mm-hmm. Yeah, and out of kind of necessity of, holy cow, this is too many marks to make, so let's come up with some different symbols. Yeah, cool. All right, who's next?
Okay. Is he gone? Clay, here you go.
What I find interesting is that like the calculator they use, like each country, like different country use different calculator. Like China use the counting, which they use yin and yang, which is male, female, and other kind of stuff.
Yeah, and the different knots and the abacus and all those sorts of things. Very interesting. Awesome. All right, who's next?
Let's go with let's Betty.
I kind of find interesting, like when they discovered irrational numbers and like rational numbers, like how they categorize that. I don't know how they figured that out, but yeah.
Okay. Yeah, the different groups of numbers, and when we start grouping things like that, then we can come up with properties of those numbers and all sorts of stuff. Very, very cool. And the one thing that I got out of that video at the beginning, it talked about the pure math and then the applied math, and sometimes we get so concerned about applying the math that we forget about, okay, let's just figure out what's going on here, and then some of those things, their applications come a little bit later down the road, which is pretty interesting to think about. All right, who's next?
Lilia.
I learned that many countries use different symbols for their numbers and everything. Yeah.
Yep. Some of which we still see today, and like the Roman numerals. You don't see them maybe as much, but for some reason they stick around on some clocks. We see Roman numerals on clocks, and the number of the Super Bowls, and a few other places. But yeah, it is very interesting stuff. All right, who's next?
Sava.
I thought it was interesting how teachers that have math anxiety can spread it to their students.
Yeah, that's something that actually high school teachers, we've talked about a number of times, how important it is that elementary teachers have a very good and positive attitude about math, because yeah, it's spreadable, and that's something that we definitely don't want spreading, because it can affect those students all the way through, as they might be more anxious about math, or think that they're not math people, or that they're just always going to be bad at math or whatever. So yeah, definitely. All right, did we get everybody? I think so. Awesome. It's always great to hear from all of you, and hear what you found interesting. And I hope that there was some stuff, even other things that you didn't share, that you found interesting in those videos. I thought they did a nice job of sharing some of that stuff, and just giving us a little bigger picture and idea how math came together, and when it started, and why some of the things are what they are. So then I will put links to those videos in Google Classroom. If you want to go back, or if you want to show somebody something that you thought was cool or whatever, you can certainly do that. And remember, we've got the Wrapping Up Mathagon Khan Academy, and then the survey for this week's assignments in there. And if you don't have any questions, you'll be out of here. I will see you on Wednesday. If you do have any individual questions, feel free to stick around. Otherwise, I think we'll call it a day. Have an awesome one, and I will see you on Wednesday. Do you have a question about something, Betty?